Alright, in this video we're going to tackle some of the slightly more complicated solubility equilibrium problems. These are involving the forming of precipitates. We'll start with a question that's really just a review from the first year chemistry course, grade 11 chemistry. It says 1 molar solutions of the following salts are mixed together, in which cases would a precipitate likely form? One of the things that makes this problem easier is the fact that these are very concentrated solutions. So what we're going to do is simply look at the two salts that are given here. We're going to apply our rules that we learned back in our first year course, general solubility rules. Okay, things like most alkali metal salts and ammonium salts are soluble, therefore they don't form precipitates. Nitrate salts, acetate salts are also very soluble. They also don't form precipitates. Silver acetate is moderately soluble. Chlorides, bromides, iodide salts are all very soluble unless they're bonded to silver, lead, or mercury. So silver, chloride, lead, bromide, those would form precipitates, for example. Sulfate salts are also soluble, except for silver, lead, mercury, calcium, strontium, barium as well. So these are the rules. You may have some of them memorized. I would suggest memorizing at least the first 3 rules regarding alkali metals, ammonium salts, the nitrates, and the chloride, bromide, iodide salts. Those are very commonly encountered situations that are worthwhile memorizing. So if we look at the first question here, we're mixing 1 molar solutions of sodium chloride and copper 2 sulfate. If you think about this, when we mix them, a double replacement reaction may occur. So we're going to get sodium sulfate, which is Na2SO4, and copper chloride, copper 2 chloride, CuCl2. So those are the 2 salts which might form as a result of mixing. However, when we look at both of those salts, we notice that according to those rules, these are both highly soluble salts. The sodium sulfate has sodium, an alkali metal. Copper chloride has chloride, and copper is not one of the exceptions for chloride. So neither one of these would form a precipitate. In fact, you mix these 2 solutions, and you're really going to have just 4 ions floating around in the resulting mixture. You'll have sodium chloride, copper, and sulfate ions all floating around without any precipitate forming. Lead nitrate, potassium nitrate, well, this one's a bit of a trick. When you mix them, you're just going to get lead nitrate and potassium nitrate, so really there's no precipitate forming. Nitrate salts are highly soluble. Silver nitrate, sodium sulfate. We can do this in our head. Silver sulfate is going to be something that's not very soluble, so if 1 molar solutions mixed, you're likely going to see a precipitate of silver sulfate. So Ag2SO4. Sodium nitrate, by first rule and second rule, sodium and nitrate is not going to be a precipitate. It's highly soluble. So this is the salt that might precipitate in the third situation. In the last situation, we have lead nitrate, potassium bromide. When mixed, we get potassium nitrate, which is highly soluble, and then lead 2 bromide, which is not very soluble. So lead 2 bromide is likely going to precipitate. And we're getting these answers just by knowing the solubility rules and a little bit of knowledge about how to write chemical formulas, right? Now, the next question is a little bit more quantitative. It's not just asking, is precipitate likely to form? It's asking whether the precipitate will form or not. So we have to be very concrete now. Will a precipitate form when 20 milliliters of 0.01 molar silver nitrate is mixed with 2 liters of 0.002 molar potassium chromate? The KSP of silver chromate is 1.1 times 10 to the minus 12. Now, when you mix these 2 solutions, by the logic that we were using above, we can see that one of the products is silver chromate. And silver chromate is clearly not very soluble. It's got a very small KSP. So silver chromate might precipitate. The question is, will it precipitate? Well, that's going to depend actually not on just the solubility rules. Silver chromate's not very soluble, but we have to be quantitative now. We have to actually answer the question mathematically. So let's think about this for a minute. Silver chromate, Ag2CrO4. If we think about we're going to get a precipitate forming. So that's the key. We have to calculate Q and decide if Q is bigger than or equal to or less than the KSP value. If Q is bigger than KSP, we get a reverse shift and a precipitate forms. So let's calculate what Q is. Well, to find Q, we're going to have to know the concentration of silver, and we're going to have to know the concentration of chromate. So the silver concentration, the question said 20 mils of 0.01 molar silver nitrate. So in there's going to be 0.01 molar silver, but it's mixed with 2 liters of 0.002 molar potassium chromate. So we have a dilution we have to worry about. Dilution, C1V1 divided by V2, that's how we calculate the concentration after dilution. So we have the original concentration, 0.010 molar, times the original volume, which was 20 milliliters. Now the new volume, V2, is going to be the 2 liters, or 2,000 milliliters, plus the 20 milliliters that were added. So 2,020 milliliters. V2 is not just the second volume, it's the total volume after you've diluted. So grabbing a calculator, we can quickly find the silver concentration, 0.01 times 20 divided by 2020. It's 9.9 times 10 to the minus 5. So we have a very small concentration of silver. Now let's do the same thing for the chromate. The chromate was 0.002 molar, and its formula K2CrO4, so there's 0.002 molar chromate in that solution. So we're going to do the same thing, C1V1 over V2. So 0.0020 molar, that was the original concentration, times 2,000 milliliters, we had 2 liters of the solution, divided by the final volume, 2,020 milliliters. So 0.002 times 2,000 divided by 2,020. So this is not going to be diluted very much. In fact, 0.00198. So if we round that off, we'll call it 0.0020 again. Well, I guess, no, I'm going to keep just 2 sig figs. So 0.0020 molar. So it is diluted, but so little that its concentration effectively doesn't change. So now we can calculate Q. We calculate Q the same way we calculate KSP, so concentration of silver squared times the concentration of chromate. So the silver concentration, 9.9 times 10 to the minus 5 squared times the concentration of chromate, 0.0020. So QSP doesn't really matter, but 9.9 times 10 to the minus 5 squared times 0.002. 2.0, I guess, times 10 to the minus 11. That's very close, but when we look at the KSP, we get 1.1 times 10 to the minus 12. And so the QSP is indeed slightly bigger than KSP. So since QSP is greater than KSP, yes, a precipitate will form. Now understand there's two other logical results that we might have encountered here. It's possible that QSP would be equal to the KSP. What would that mean? Well, that's very unlikely, first of all, but if it does happen, then it means that your solution is actually saturated. If the QSP equals the KSP, you're at equilibrium, and in solubility terms, that means the solution is saturated. In that situation, we would say that no, a precipitate doesn't form, but the solution is saturated. The third possibility would be that Q is less than KSP. If Q were less than KSP, now normally that would mean a forward shift would occur. But in this situation, that can't be true. Can you see why? For a forward shift to occur, there would have to be some silver chromate. There isn't, right? Silver chromate is possibly forming in the reaction, but it's not there initially. So what we would say in that third situation, if Q is less than K, is simply that the solution is not yet saturated. The concentration of silver and chromate is low enough that the solution is not saturated, and therefore no, a precipitate does not form. So three possible results. Q is bigger than KSP, you do see a precipitate. Q is equal to KSP, you're at equilibrium, the solution is saturated, there is no precipitate. If Q is less than KSP, the solution is not saturated, and again, there's no precipitate that forms. Alright, so let's try. You can pause the video if you think you understand what you're doing now, and try this next question. So it's very similar to the last one, but this time instead of mixing two solutions together, we're adding a solid. We're adding half a gram of lead nitrate to 500 mils of potassium chloride. And we have a KSP for lead, for lead chloride given in the question. So lead chloride is the substance which might precipitate. So if we look at PbCl2, we can see that it's KSP, 1.7 times 10 to the minus 5 is equal to the concentration of lead times the concentration of chloride squared. So what we need is both the lead and the chloride concentrations. Let's go get the lead concentration. So we have half a gram, 0.50 grams, of the lead nitrate. If we get rid of the grams and switch to moles of lead nitrate, using the molar mass, we can switch from moles of lead nitrate to moles of lead, using just the formula. And then 500 mils is 0.5 liters. So if we just divide the moles by 0.5 liters, we'd have the concentration. So the first unit multiplier is the molar mass of lead nitrate, 1 mole using periodic table, 331.22 grams. The formula for lead nitrate has 1 lead in it, so 1 mole of lead nitrate has 1 mole of lead. And now grabbing a calculator, 0.5 grams divided by 331.22, and then divide by 0.5, 0.0030. And that'll be molarity of lead in that solution. Now let's go get the concentration of chloride, which should be a little bit easier. For the chloride, we'll have to make a small assumption. In the previous question, we were mixing two solutions, and therefore the volume definitely changed. Here, we're mixing half a gram of a solid salt into 500 mils of solution. We'll assume volume is constant. If the volume is constant, then there is no dilution, so the concentration of chloride is right out of the question. It's going to be 0.0075 molarity. In the formula for potassium chloride, there's one chloride, so in a solution of 0.0075 molar potassium chloride, there's 0.0075 molar chloride floating around. So now we can calculate QSP. It's going to equal the concentration of lead, 0.0030, times the concentration of chloride squared. So the QSP here is going to be quite small, 0.003 times 0.0075 squared, 1.7 times 10 to the minus 7. And so if we look at the KSP, it was 10 to the minus 5. So we can say here, since the QSP is less than the KSP, no precipitate will form. The solution is not saturated. Okay. All right. The third problem is a little bit different. Pause the video and see if you can figure out how it's different. So what mass of calcium chloride do we need to start precipitating calcium carbonate from a 100 ml solution of 0.05 molar sodium carbonate? And we have the KSP for calcium carbonate. So if we make sure we understand what the question's asking, we have 100 mils of 0.05 molar sodium carbonate solution. And into this solution, we're going to add some calcium chloride. The question's asking us, what mass of calcium chloride should we add to start precipitating calcium carbonate? Calcium carbonate is not very soluble, as we can see from its small KSP value. So when we add calcium chloride to the solution of sodium carbonate, we can imagine calcium carbonate forming, and therefore a precipitate forming. The question is, what mass of calcium chloride will start that precipitation? It's probably not going to be a large mass, because the KSP of calcium chloride is so small, it's going to require very little calcium chloride to start the precipitating. But how do we actually answer that? Well, again, we'll assume no volume change, which means the concentration of carbonate in the solution is equal to, from the sodium carbonate, 0.05 molar. The question is actually quite simple to solve. What we'll do is we'll take the KSP, which was 3.4 times 10 to the minus 9, and we know that's equal to the concentration of calcium times carbonate. And we realize in this KSP expression, we know the concentration of carbonate. It's 0.05. So we can calculate the concentration of calcium needed to make the solution saturated. So the concentration of calcium to saturate the solution would be the KSP divided by the carbonate concentration. And calculating that real quick, 3.4 times 10 to the minus 9 divided by 0.05, 6.8 times 10 to the minus 8 molarity calcium. So understand what we've just calculated. In a solution of carbonate, 0.05 molar, you would need very tiny, 6.8 times 10 to the minus 8 molarity calcium to make that solution saturated. Any more than this, and the solution will start to precipitate, calcium carbonate. Why would it start to precipitate? Because if you have a greater concentration of calcium than this, your QSP is going to be bigger than the KSP. So now what we'll do is simply take the volume of the solution. We had 100 milliliters. We'll switch the milliliters to liters. We'll switch liters to moles of calcium. Moles of calcium to moles of calcium chloride, and finally moles of calcium chloride to grams of calcium chloride. Does that make sense to you? So 1 liter is 1,000 milliliters. We just found 6.8 times 10 to the minus 9, that's right, 10 to the minus 8 moles per liter. The formula for calcium chloride says a mole of it has a mole of calcium. And then the molar mass of calcium chloride, 110.98 grams per mole. So 0.1, 100 divided by 1,000, times 6.8 times 10 to the minus 8, times 110.98. It's going to be a very tiny mass, equals 7.5 times 10 to the minus 7 grams of calcium chloride. That is such a small amount, it's hard to imagine it. So basically the tiniest smidgen of calcium chloride added to that solution, we should see chalky calcium carbonate precipitate forming. So this many grams of calcium chloride will start the precipitate. Now technically this amount of calcium chloride makes the solution saturated, and so what we technically should say is any mass greater than this will cause the precipitate to form. This is the mass to make the solution saturated. Alright, let's look at one last problem here. A little bit different. There's no calculations required in this problem. See if you can pause the video and answer it yourself. You'll need access to a table of KSP values. So we have a 0.1 molar lead nitrate solution. We're adding dropwise to 50 milliliter samples of sodium chloride, sodium hydroxide, potassium bromide. In which solution will a lead-based precipitate form first? We know when we mix lead nitrate with these solutions, we're going to get, in the first case, PbCl2 forming, in the second case, PbOH2, lead hydroxide, and then in the third case, PbBr2. So those are the three possible precipitates that will form. Notice that they all have the same basic formula with 3 ions. That's very important to solving this problem easily. Because these 3 salts have the same basic formula, they all have 3 ions, 1 lead and 2 anions, 1 lead and 2 anions, it means that mathematically they're all going to be treated the same way. If you've done some KSP problems, you know that with 3 ions like that, you always get a situation that says KSP equals 4s cubed. The point is that because the salts have the same number of ions, we can judge their solubilities based on their KSP values. So if we look at lead chloride, its KSP value, looking it up in a KSP chart, lead Fluoride, 1.7 times 10 to the minus 5. Lead hydroxide, its KSP value is 1.4 times 10 to the minus 20. Wow, very, very tiny. The third situation, lead bromide, its KSP value is 6.6 times 10 to the minus 6. So if you're adding the lead nitrate solution drop-wise, so dropping it from an eyedropper or something, or a burette, into 50 ml beakers of each of these solutions, in which solution would a precipitate form first? Well, it'll form first in the solution where the lead salt is least soluble. And again, since they all have the same basic formula with 3 ions, we can judge their solubilities just from their KSP values, and lead hydroxide is clearly the least soluble of those 3 salts. It has by far the smallest KSP value. Now again, if these salts had different formulas, if one of them had only 2 ions instead of 3, or one of them had 4 ions, then we'd actually have to calculate the calculate the solubilities in each case to judge the solubility, to rank their solubilities. So in this case, it was easy to solve without any calculations. The least soluble salt is the one that's going to precipitate first, so lead hydroxide. So there you have it, a range of solubility problems involving the forming of precipitates.